to if you have questions, or if you want to stop and just turn your mic on and ask a question, that's fine too. I see Evan is in the chat. Perfect. Okay, so let's get started with today's lesson. So we are looking at pre-algebra, right? What is pre-algebra? Pre-algebra is a connection between arithmetic, which what you're probably used to, addition, subtraction, multiplication, and division. And then that bridges it. Pre-algebra will take us from that to algebra, which algebra is the same kinds of things, addition, subtraction, multiplication, but it's more abstract. We don't use just numbers. We often use letters or variables to work with that. So before we, if you want to have a good foundation in math, it's nice to understand where the math comes from or why you're doing something rather than just being able to do it. All right. I could give you a bunch of rules and you could follow the rules, but you might not understand why the rules are the rules. So that's the plan for today, is to look at some of these properties that you may or may not understand already and go over some of the basics of arithmetic. So we're going to start at looking at the properties of addition, but before we get there, we want to just talk about a little bit of terminology. Everybody can see my screen, hopefully. So we have this sort of number line here, and on the number line, we have what are called integers, right? These are integers because they're whole numbers only. There's no fractions or decimals, right? So you have 1, 2, 3 on the right side, and on the left side you have -1, -2, -3. There's just been, some debate between people in math about what kind of, what names should we call these things. We have, some people call them whole numbers. What's a whole number, right? Officially, I believe a whole number is 0, 1, 2, 3, 4, 5, all the way up. And then we have what's called natural numbers, right? Natural numbers. What's a natural number? Well, natural number, it just doesn't include 0. So it goes 1, 2, 3, 4, 5, but no 0. And often people will confuse those. And so, some people think the natural numbers have 0 and some people think they don't have 0. So we're not going to use those terms. The book we're going to be working from uses what are called positive integers. So the positive integers would be all of these numbers, right? And so forth, because they keep on going. Those are the positive integers. And then we can also use what's called the non-negative integers. So non-negative, meaning including 0, right? So non-negative stuff. So we have positive integers or non-negative integers, which would include 0. So if we add this in, now when we include 0, instead of calling them the whole numbers, we're just going to call them the non-negative, right? So non-negative integers. Okay, so we basically look at these, we're going to look at all these properties using problems to bring that out. And then we're going to examine the problem, see how we could explain the problem, and then develop the rule from there. And then we'll apply those rules to some practice problems. And hopefully, you'll have a better understanding of some of the underlying principles of math And then once you build, if you have a good foundation in math, then you can, expand to all kinds of things. So here's the first question we're going to look at. Using the pictures, explain why 2 plus 3 equals 3 plus 2. Okay, well, what does that mean? All right, how are we going to use the pictures to explain why 2 plus 3 equals 3 plus 2? Well, on the left side, right, if we look at this diagram has 2 rows, right? And the first row has 2, and the second row has 3. And so there are 5 blocks altogether, 5 squares, 2 plus 3, right? Whereas on the other side, this picture has 2 rows again, but 3 blocks plus 2 blocks, but there's still 5 blocks altogether, right? Both sides have 5. There are 5 blocks over here and 5 blocks over there. We just turn this picture upside down, right? If you look at this diagram on the left, it's just a flip. It's just this one upside down, right? But turning it upside down doesn't change how many blocks there are. There's still 5, right? So 2 on top of 3 or 3 on top of 2, same 5 blocks, right? That's a super important property that you might just, already know that it's obvious that 2 plus 3 equals 3 plus 2. But this is called in, let me just put text up here. Does anyone know what this property is called? I don't know. That's a good question, right? Do we know what this property is called? I'm guessing you don't, so I'm just going to tell you. This is what's called the commutative property. All right. So if you take any 2 numbers and you add them together, and then you can flip them, you can reverse them, right? It's called the commutative property of addition. So addition is what's called commutative, right? If I take 2 numbers, so it doesn't have to be 2 and 3, it can be 4 plus 6, right? You can write that as 6 plus 4. You're still going to end up with, right? Obviously 4 plus 6, everyone knows what that is, or 6 plus 4, right? Still gonna end up with 10, right? We still get 10 on both sides. And so the commutative property, so it's gonna help us, or why are we gonna learn these properties? It's gonna help us do a lot of mental math when it's easier to commute something, and then we can add it the opposite way. So that's the first one, right? And so you can make this into, not just any 2 numbers, right? So we could make the rule, which really says this. If I have a number P, all right, we have what these things are called letters. This is sort of jumping to algebra, but these are letters, right? Representing numbers. So if you take any 2 numbers, integers, positive integers, P plus Q is going to be the same as Q plus P. It's called the commutative property. Addition.
It's like you know what it is, but you also don't know what numbers are, but you know they equal because they're the exact
because you
same.
could, yes, right. You
It's
can
like
take
thing and a thing.
exactly, and we just let things represent numbers, right? That's really what algebra is. The letters represent the numbers, right? And so if you take any 2 numbers, 4 plus 6, pick any 2 numbers you want, you can add them in the opposite order, right? You can turn the order around, you're still going to have the same. And so you get this sort of rule where P and Q are just numbers. P and Q are just numbers, right? So P plus Q equals Q plus P. They're not, part of the alphabet, obviously. They're just representing numbers. And that's really, they're called variables, right? When we have, it's called a variable because it can change. P can be any number we want, and Q can be any other number, and they could be the same number, it doesn't matter. But if you add them in the opposite order, you're going to get the same thing. So that's property number one, which is the commutative property for addition. Is that okay, Philip?
Technically, if P was a number and Q was a number, couldn't it just be P plus P equals P plus P?
Yeah, you could. They can be the same number. I said that's also a possibility, right? You can have the same number because if we take it, just like 3 plus 3, right? 3 plus 3 is still 3 plus 3. Even, when you reverse it, you can't really tell that it's reversed because of the same number, right? So it's still going to be the same. Okay, so that's property one. So we're going to try to remember these properties when we get down to work on some practice problems, right? So let's look at property number two. So this question asks us to look at these two pictures and explain why this is true. Why is this true? And you may remember, or you may know, that when you have brackets or parentheses, you're supposed to do that operation first, right? You do the parentheses, what to calculate first. So, if we work out the math on both sides, what's the answer to the math on both sides here? 2 plus 3 plus 4. Everybody can do 2 plus 3 plus 4?
9.
It's 9. Yes, Philip, thank you. That was Philip, right?
Yes.
So we have 9, right? We know the answer is 9, but we're going to use the pictures to explain this, right? It's not a proof, but it just helps us understand what the property is, right? So if we start with the left side, right? We have 3 rows. If we count the clear squares first, the white squares, right? We're going to count the white squares, and then we're going to count the dark squares or the shaded squares, right? So on the left side, we have 2 plus 3 white light squares, right? So we have 2 plus 3 white squares, and then we have 4 dark squares, right? So these are the light squares. And these are the dark squares over here. So we have 2 plus 3 light squares plus 4 dark squares. What about the other one? On this side, right? If we count the light squares first, we are going to have 2 light squares, right? We start with 2 light squares, and then we have 3 plus 4 dark squares. All right. Both sides have the same amount of squares. Both sides have the same amount of squares. There are 9 squares on both sides. But we can add them differently, right? We can add the light squares first, 2 plus 3, and then add the 4 dark squares. Or we can start with the 2 light squares and then add the dark squares first, 3 plus 4, and get 7 dark squares, and then add the 2 light squares on, and we get 9. But so it doesn't, whether we add the light squares first or we add the dark squares first, the total number of squares is still 9. And that's what this property is. If you notice, only the middle row is changed, right? We changed the middle row color. Changing the middle row color doesn't change how many squares we have. Right? Changing the middle row color, we still have 9 squares altogether. And so what it tells us is what's called the associative property. This is called the associative property of addition. So very important again. Let's go text here. So the associative associative property. It just means you can, if it's addition, you can put the brackets around whatever piece you want. You can either add the first two and then the third one, or we can add the last two and then add the first one on after. So you can reassociate. So associative property, you can reassociate what's going on here, right? So you can just move the brackets and you still be the same. 9 on both sides, whether you add the 2 and the 3 first, or if you add the 3 and the 4 first. Okay. So having the associative property along with the commutative property, okay, and we can change this again to A's and B's and C's, right? We can write this, and so the associative property really says this, right? If I go and do this, I can get some algebra going here again. So I can do A plus B. Oops, that's supposed to be plus. So that's the associative property of addition, right? So you can group them, regroup them. You can have A plus B or plus C or A plus B plus C. So you can group them. And again, important for helping us do mental math, right? We want to do a lot of mental math. When we're trying to be good math students, we don't want to rely on technology to give us the answers, right? So we want to be able to do some mental math. So we want to use the properties to answer this question, right? Explain why this is true. 472 plus 219 plus 28 equals 472 plus 28 plus 219. Okay, well, let's start with the left side. Right? So we just, you want to be able to explain why this works. And a lot of it might be, I don't know, easy to see the answer, but not so easy to see what rule we use, right? So if we start with this, 472 plus 219 plus 28, all right, the first thing we could do here is we could use the commutative property to rewrite, all right? I can rewrite what's in the brackets the opposite way, right? I can write it as 28
first. I put
right.
like 472 plus 28, and that gets you like 500 exactly.
Oh yeah, I don't want to calculate the answer. I understand where you're going. We're going to calculate the answer shortly, but we need to, eventually we're just going to be able to apply the rules because we know they work. But I'm just trying to show you what the rules are first. So I can do this, right? Why can I write it like that? All right, I can do that because that's the commutative property, right? Commutative property says you can add things in the opposite order. So 28 plus 219, right? 219 plus 28. We can flip that. Then we can do one more line here and we can say, okay, now I'm going to associate. I'm going to change the association, right? I know I can group them any way I want. And so I can then say, okay, this is going to be 472. And I'm going to add that to the 28 instead first. And then I'm going to add the 219 at the end, right? So I put the parentheses around the first two instead of the last two. And that's application of the associative property, right? All right, so now, why is it nice to do it that way? Well, if we're trying to do mental math, it's a little bit hard to add 219 and 28. It's a little easier to add 472 plus 28. Why is that easier? What's the answer to 472 plus 28? Can we do it in our heads?
500.
500? This is just me and you working here, Phil. It's 500. Yes.
Oh my, everyone left. I mean, everyone like left their camera.
No, I'm just saying you are giving me all the answers, which is cool. Everybody else is still here. They don't have their camera on. I think they're still here, hopefully. So 472 plus 28 is 500. It's nice and neat, right? So I can reassociate that, do some mental math, get 500, and then I can add 219, right? It's not too bad to add 500 onto 219. What do we get for an answer?
719.
Right, 719, right? So that makes it, fairly nice to do that. So, but working on mental math, super important, right? We want to be good at mental math. So that's that question. So we got two properties for addition. So, right, so far we have what's called the commutative property and the associative property. Let's look at the next example. All right. So often we won't write down, I won't go through, once we know that those properties are okay, that we know they work, we don't have to go through the list every time to say, okay, I know I can commute this and then I can reassociate with that. If you know the commutative and associative properties work, we can do a question like this a lot easier. I want to compute this using, so really what I want to do is when you have all addition, you can commute and regroup and commute and regroup and get something nice, right? What's the, does anyone have an idea about how we could solve this problem nicely or neatly?
I see that 8 plus 2 makes 10, and there's 12, 22, and 32. So if I do 2 plus 8 plus 12 plus 18 plus 22 plus 28 plus 32 plus 38, it's 2 plus 8 is 10, 12 plus 18 is 30, 22 plus 28 is 30. Wait, no, it's 50, and 32 plus 38 is 70. So 10 plus 30 plus 50 plus 70. And that's
Okay, that's one way to do it, and it's not too bad, right? I think there's a slightly easier way to do it, right? Because then you can work that out, which it isn't awful to figure that out, right? 10 plus 30 plus 50 plus 70, you could get the answer.
Or you could do 32 8 and 22 plus 18 and 22 plus 28, and that all equals 40.
Yeah, that's the one I want to. That's the one I want to use. But you're not wrong there, right? There's lots of times good ways to do problems that aren't the same as everybody else. But if we regroup these, right? If I do 2 plus 38, and then right plus 12 plus 28 plus 22 plus 18. And then plus 32 plus 8, as you noted there, Philip, those are all going to be 40, right? If we group these all. So we'd be applying the associative rule and the commutative rule a few times to get to this sort of setup, right? This is what we'd be getting to. And then we might notice that, oh, that's 40. Oh, and that's also 40. 28 plus 12 is 40. And 22 plus 18 is also 40. And 32 plus 8 is also 40. So they all come out to 40, right? And now we have 40, 40, 40, 40 all added together. That's the same as 4 times 40, or if you add them up, what's the answer to this question then? What's 4 40s?
160.
Yeah, 160, right? So 160, right? Okay. But you get
Wait,
160 also.
plus 4 plus, it's like 4 plus 4 plus 4 plus 4, and then you add a 0.
You do add a 0 there. But you could get the same from what you said earlier, right? So this other approach is just as good. You just have a little harder addition at the end, but it's all good. Okay. So the answer is 160. So when you're doing some problems like that, we're looking to make those kind of connections where it makes it easier to do the final calculation without having to get out a calculator. All right, because if you start with this, you go, okay, 2 plus 12 is 14, and then 14 plus 22 is 36, and 36 plus 32 is like, 68, and you start working your way across. That's a lot harder than if we reassociate and we get 40s, or we get 10, 30, 50, and 70. So that's not, and it's nice and neat this way. Okay, let's look at another one. So we want to find the sum of the numbers from 1 through 9 through 20, and we're going to include the ends. All right, so we're going to add 1 plus 2 plus 3 plus 4. So you could start going. 1 plus 2 is 3, right? And then 3 plus 3 is 6.
Or you could make them all like 20.
I can make them all 20?
Yeah, because 1 plus 19 is 20. 2 plus 18 is 20. 3 plus
Okay.
7 is 20.
So you want to do this. I'm happy to do that. Let's see what happens. So you say 1 plus 19. Okay. And then we're going to put the next one, what, 2 plus 18?
Yeah.
Let's write them all out and see what it looks like. And then we're going to do 3 plus 17, probably, I think.
This might take a while to write.
It's okay. I'm slow. We have time. All right. So it's a good idea. Like, problem solving is all about thinking about ideas, right? And everyone has a different idea. And maybe this one's going to be great. And maybe it's just going to be okay. I don't know. Let's find out. So then we have 4 plus 16. What's the next one going to be?
5.
Anybody else who feels like speaking up, you're welcome to talk. It's great. Or you can type in the chat box if you have that option. Go ahead, Philip. It's fine.
5 plus 15.
Okay. 5 plus 15. And then 6 plus 14.
Yeah, so I think it's going to go all the way up to 9, I think. So that
7
means...
plus, yeah, this, right. So 7 plus 13, and then 8 plus 12.
Yeah, so we know
And then
there's
9 plus 11. What am I missing now from all of my numbers?
And then you just write a 10, I guess.
Okay. Missing anything else?
And the 20. So it's basically like
right.
you have 9 20s plus the 20. So that's 20 20s, which is 400.
That's 10. Slow down. Back up.
Oh,
That's close, but you said it's 20 20s. It's only 10 20s.
yeah, 10 20s, which is 200.
Okay, so you
10.
want to say this. 10 times 20. And then you're going to add 10 to the end. Yeah, that works, right? And for those people who are maybe not following all of this, let's just explain where we got that from. We grouped these, right? 1 plus 19, that's 20. And 2 plus 18 is also 20. And 3 plus 13 is 20. And 4 plus 16 is 20. And all the way up to 9 plus 11 is 20. And so he said we have 1, 2, 3, 4, all the way up to, we have 9 20s. And then we have this extra 20 that we didn't include, which becomes the 10th 20. So we have 10 20s. If you have 10 20s, it's the same as 10 times 20. But then we left out the 10, right? It's not as nice and neat as I would like to do it, because it requires us remembering that we forgot the 10 and we forgot the 20, and then we have to work it in. But the answer is going to be the same, right? So 10 times 20 is 200 plus 10. So, the final answer is going to be 210. Another way to do this, right? So the answer is going to be 210. If we group them slightly differently, Philip, and I'm not saying your grouping is bad, I'm just saying we could group them slightly differently, right? How could I group them differently? I could do 1 plus 20 and 2 plus 19 and 3 plus 18. All the way up to, right? What would be the last pair of addition on this sort of thing?
10 plus 11.
Yeah, perfect. 10 plus 11. All right. We would have 10 plus 11 here. What does each of those sums add up to?
21.
Yeah,
So
each one is
just
21, right?
21.
How many 21s do we have?
10.
We have 10 21s, right? Because we can see we went 1, 2, 3, all the way up to 10 plus 11. And so we end up with 10 21s. Adding 21 up 10 times is the same as multiplying 21 by 10, right? So this is 10 times 21. And I don't know if you know how to multiply by 10, but you just add a 0 on the end when you multiply by 10s, right? So 10 times 21 is just 21 with a 0. So 210. So we get there the same way. I like your problem solving in the first one. Here's another way to do it. One is not better than the other. It's just different.
It's kind of like I turned it into what is it called? Friendly numbers.
Yeah, right. That is what you want to do, right? And you made yours into 20s, which is nice and neat. These are 21s, but there's 10 of them. Yours got, you had to do a little.
There were like 7 21s. That would be complicated.
Yeah, that would be harder, right? Right. Okay. So far so good, I think. Let's see next. All right. What else can they ask us to do here? So here's another thing we want to look at, which is another property. It says, can you use the picture to explain why 2 plus 0 is equal to 2? Well, it's kind of weird. It's just an explanation. It's not really, there's no proof here, right? Well, on the, in the one case,
0 is nothing.
Right. In the one case, there are 2 squares, right? There are 2 squares. So that's
and there's
fine.
an imaginary 0 square.
So let's talk about the colored squares then, right? So there are 2 squares on the total. If I can spell this properly. And if we think of the other side as 2 light squares, let's do this, all right? I have 2
0
light plus 0 dark. Right? So I have 2 light, 0 dark squares. There's no dark squares, and so we get 2. So if you add 0 to something, it doesn't change it. Right? You get the same thing back, whatever you started with. If I start with 2 and I add 0, I get the same thing back.
It's
2 plus 0 is
filler. But if it was 10, there's still a 0, but now it holds a value.
Yeah, something like that.
That makes sense. So it's like a placeholder in a way.
Yes, sort of. There's a name for this also, right? There's a name, a special name for this. It's called the identity element.
Confusion.
Identity element for addition. What does that mean? Well, it just says that 0 is the identity element for addition, right? When you get, you get the identical thing back that you started with if you add 0. That's why it's called the identity element, right? And so it just looks like this. The identity element for addition, I'll just say, is 0. Right. So you take any number, it doesn't have to be a given number. You can use algebra. We're using algebra here, right? So some number a plus 0
is still going to be a.
You just get a back, right? So you get the identical thing that you started with when you add 0, and that's why it's called the identity element for addition. There are different elements for all, not all of them, but for different operations, right? If we're talking about multiplication, which I don't know if we might get to some of that today, we might not. There is associative and commutative, and there's an identity element for multiplication also. So if you add 0 to some number, you get the same number back. That's called the identity element. Okay, so let's flip to another question. So here's some practice problems, right? Some practice problems. We want to use either the identity element or the associative or the commutative properties, to make this nicer to figure out. 99 plus 99 plus 99 plus 101 plus 100. So what's a good way to do this question?
99 plus 101 is 200, and there are 3 of them, which is like 203. No, wait, 302s. I mean, 300. Wait.
Slow down. Don't go too fast. You got great ideas, but don't go too fast. All right. So we're gonna say
3 200s. Yeah,
that's right. Right, and we'll get to that in 1 second. But we're gonna regroup these associatively and commutative, right? We're gonna commute the 99 and the 101 and then commute the next 99. So we get them over and we're just gonna reshuffle them and they'll be able to look like this. Right. When you have addition, you can reshuffle them pretty much any way you want, forwards and backwards, and then reassociate, right? The reassociation helps us because each of those 399s and 3201s, each of those has a sum of 200, as you said. Right. So
yeah, so there's 3 200.
Right. So what's the answer?
It's basically 2 times 3 add 2. It's basically 2 times 3, and then you add 2 zeros, which is
what?
600.
Right. It comes with a 600, right? I have 3, and that's another thing that we're going to get to, right? Multiplication is just repeated addition, right? If you have addition repeated, 200 plus 200 plus 200, that's just multiplication, right? Multiplication is, I've got 3 times 200 then, because I have 200 added together 3 times. So we get multiplication, which equals 600. But that's, we're going to get to that. Does anybody else have a question or a comment that they want to mention? Philip and I are dominating the conversation here, so. Sorry. I see you people actually answered. Alfie and Evan, you answered 9 in the chat box. Thank you. I didn't even notice that when we were doing the other question about how many squares there were. Very good. Okay. Then let's go on to another problem then. How about this one? Compute 1999 plus 2001 plus 1999 plus 2001. Okay. Go ahead. I want to let people think about it for a second before we actually, some of us will be faster at analyzing the question and going, this is what we should do. We just want to let people just think about it. Oh, good. Okay, it's 3,004 different times. That's close, Evan. Real close. What's the little mistake that Evan made?
It's 4,000.
It's 4,000, not 3,000.
It's
That's a
because
minor mistake.
if you add 1 to 1,999, you're going to get
Yeah.
2,000 and subtract 1 from 2001. It's 2,000 plus 2,000, which is 4,000.
Right. It's 4,000, but Evan, that's an excellent effort there. Just a minor mistake, right? So this is 4,000. So we're going to regroup these, right? We're going to regroup these like this. So when we regroup them, then you might notice, and a good way to do that was take the 1 from here and you put it onto 1999, and you get 2,000. Right? If we take and we say, oh, we're going to put that over here, then we have 2,000 on each piece, 2,000 plus 2,000, which is 4,000. And so we'll get 2,000 plus 2,000. Good to see you there, Evan. I see your camera's working. 4,000, right? So, and as Evan said, there are 4 of those, right? There are 4, right? 4 times. So repeated addition, we're adding this, right? Repeating the same thing 4 times is just multiplication. And so we end up by using the associative property here, associating these things in pairs. 4 4,000s, what's the answer to that? Did you write that up, Evan? 4 times 4,000?
Oh my, wow.
Yeah, 16,000, right? Good.
Wow.
4 times 4 is 16, and then throw the zeros on the end. Save the 3 zeros. And so we have 16,000.
0, 0, 0.
Right. Okay. So that's, another question. Let's see what else we have. How about this one? This is similar to the one we did earlier. Right. We're still looking for patterns and ways that we can associate the numbers here, right? How can we associate these numbers? You start looking at the numbers and you go, I could do 3 plus 7. I could do 13 plus 17.
Okay, got this.
All right. But if we do it the other way, all right, what if we do 47 plus 3 and 37 plus 13 and 27? Right? We want to regroup.
There are 5 for every single one that ends in the same number. So it's kind of like there are 5 of whatever numbers you guys that you add together. So like 43 plus 7 is 50. So we know all of them will be 50, and they're 5.
Well,
so that
I don't think we know all of them are 50 for sure. They just happen to be 50, right? Just because 3 plus 47 is 50 doesn't necessarily make the next 2 go together to be 50, but they do actually do that. But you still have to write. You still have to write them out and make sure that they come out to 50, right?
Yeah,
so you just want to see.
But
you want to check. But we know we're looking for patterns here to make the math easier for us.
Oh yeah, he did 30. He did basically 10 plus 30 plus 50 plus 70 plus 90. Evan.
Oh yeah, right. That's also fine, but then you've got to add up those, right? After you get those, so you have 10 plus 30 plus
tiny bit harder than just 50 times 5.
Well, that's the way you did the last time, right, Philip? So you did it the same way as Evan's doing it right now.
Yeah, I used to do it like that. I mean, like,
yeah,
it's not necessarily wrong, but like
it's definitely not wrong. It's just a different way to see the problem, right? And so in this case, as we see what happens here, right, we're going to group all these, and when we group these, they all group to 50, right? So how many 50s do we get? Right, we got a 50 here and another 50. And then, another 50 over here. I believe we have 5 of them, as you pointed out earlier, Philip. All right, so we have 5 50s.
Yeah.
And then we're going to group these, and we have 50. And so there are 5 of them. 5 times 50. What's the answer to 5 times 50?
250.
Yeah, every first number is 20 less than the second one. Yeah, I saw that. Right. So if we were looking at it like Evan did, which is to add them up, we're getting 10
Which I used to do.
plus 30. Yeah, it's okay. Plus 50 plus 70 plus 90. Right. If we add up the first term with the first term and the second term with the second one and the third one with the third one. And then we can regroup those if we want, right? If we want to regroup those, we could then write that as something nice and neat like 10 plus 90. Right? We can reassociate these 10 plus 90 plus 30 plus 70, 50. Right? We can regroup those like that. Why is that nice and cool? Because we have this is a grouping and this is a grouping, and both of those groupings add up to what? What's 10 plus 90 and 30 plus 70? Right? 10 plus 90 is 100 and 30 plus 70 is 100. So now we can make it easier on ourselves. 100 plus 100 plus 50 is still 250, right? So we're still applying in both problem-solving methods here, associative rule and commutative property. And so as long as you're applying those to make the addition better for you or easier for you, yeah, that's okay. We can wait for you if you want. So that's what's that's really what we want to, we want to understand why we can do that, why we can group them in certain ways. Those are those 2 properties, right? Associative and commutative. And then we want to group them in such a way to make it easier to calculate, whether it be all 50s or 10 plus 30 plus 50 plus 70 plus 90, and then regrouping those to make it nice and neat with 100 plus 100 plus 50. Okay, so let's have a look at the next question. So here's another problem where we want to use our commutative and associative properties to regroup, right?
So it's
What's a good way to
0 to 90, it was 1 to 99, and then but there's 2 50s.
1 to 99 and 2 50s?
That's basically
Okay, yeah, that's true. It's 1 to 99 and there's 2 50s. Okay, what's a good way to group these numbers?
maybe the 1 plus 99, 2 plus 98, all the way
Yeah,
to 50. So that means
right.
there are 50 100s, essentially.
That's correct. So, no, perfect. That's perfectly right.
Because
So
now there are 2 50s instead of 1.
instead of 1 when you had that 10 issue last time, right? So you had to mess that up. So yeah, this is we're gonna add, right? We're gonna group these as 1 plus 99.
Hopefully you're not going to write that all.
No, you don't want to wait for me to write all that? No, I'm not going to write all that. And 2 plus 98, I'm going to write like 3 of them, right? Or 3 at the beginning and 3 at the end. 2 plus 98. But yeah, not everybody can see it in their head like you can, Philip. So we just want to make sure everyone's seeing what we're doing here. So 3 plus 97, right? And then if we continued, there are 50 additions here, right? So we got plus dot 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 plus 49 plus 51. 51, and then 50 plus 50 is the last one, right?
Yeah.
And each one of those additions is how much?
100. So
Right.
there,
Each one of these comes out to 100, right? So there's 100 here, plus another 100, plus another 100. That's the third 100, and we're going up to how many hundreds? Up to the last one, which is the first digit is how many, right? 1, 2, 3, 49, 50. So there are then, as you said, 50 hundreds, right? Or 100 times 50. Either way, 50 times 100. All right, and what's
yeah,
the answer to that going to be?
3 zeros. So it's basically 5,000.
You're back with 5,000 as an answer, Evan. Thank you. 5,000. Good. 5,000. Right. So again, when we're dealing with some addition problems and we don't want to have to use a calculator, we can look for patterns. We can apply the associative property and the commutative property to regroup things. And you know, it would take a lot of writing to regroup all of these additions to make it look like the first line that I wrote. But we're allowed to do that because of those rules, right? And it's always important to know why you can do such a thing, right? So why is it we can do this? Well, I tried to show you earlier those rules that allow us to do that. So the total here is 5,000. So that's properties of addition. I mean, we have a few more minutes left in this demonstration, so we can get started a little bit on properties of multiplication, and then we'll wrap it up for today and just see how that goes. So properties of addition, right? So again, we want to know, we're dealing with arithmetic, right? Because we're trying to build the foundation so we can get into pre-algebra, so then you can get into algebra, right? And number systems have properties. And at some point, you know, maybe we'll have a new operation, right? Like way down the road in math, you might find out that there's a new operation that looks like this, like a little asterisk, right?
What is an asterisk? What
Well, we
is
don't know, but you can develop. This is what happens, right? You get these things that have properties, and so you might say that that's equal to, you know, maybe that's equal to 21 minus 10. I'm just making this up, but right, maybe that equals 21 minus 10. And so you figure out what that operation is, right? It's not addition, it's not subtraction, right? It's
it's
not
the answer
multiplication.
plus 1? Because 21 minus
Well, I mean, you know, it's different things. I made it out to be this. If I do P and Q, right? I made it out to be this. So P asterisk Q, it always gives you this. It gives you P times Q minus P plus Q. I just made that up, but this might have some, you know, properties to this operation. And we're just trying to build all the properties for the operations we know. Like this, that kind of math that I just wrote is way, way down the line. That's like university level kind of stuff, where there's a whole course in talking about new ways to deal with numbers. So we just want to understand where these things come from, right? So we've looked at multiplication properties. And so now let's look at some, so we've looked at addition properties, multiplication properties. Okay. So we want to look at these two photos, two pictures, right? And explain why.
this thing again, but with multiplication.
Yeah, it's with multiplication, right? So we're trying to show why 2 times 3 equals 3 times 2. All right. Well, in the first example, there are 2 rows, right? 2 rows. And there are 3 squares per row. Right? So we have 2 times 3 here, 2 squares, for a total of 6 squares, right? So 2 rows, 3 squares each. So we have 2 times 3 squares. We have 6 squares. That's on the left side. Yeah, so we're down to like 3 minutes here, so we will we'll wrap it up shortly. But on the right side,
there are 3 rows of 2.
right,
And
there
if
are
you
3 rows.
like that, it's basically like they're the exact same numbers and there's the exact same operation. So
Right, and
kind
if you look at the picture, right, it's just
look
turned
at
on
it.
its side.
Yeah.
If I turn the first picture, I get the second picture, and there's still 6 squares, right? We can't
Yes.
change the fact. It doesn't change the number of squares just because we turn the picture on its side. And so there are 3 rows and 2 squares on each row, so we have 3 times 2, which is also 6. And this is called the commutative property, right? This is the commutative property for multiplication, right? So again, there's a commutative property for addition and multiplication. Property, I need a Y there. The commutative property for multiplication really says if I have 2 numbers, all right, I can just write this down. Right? If I have something like P multiplied by Q is the same as Q multiplied by B. You can commute it. You can multiply it the other way. So, you know, kind of interesting, right? It's the same property. So that gives us a reason why we know we can reverse the multiplication like that. So, yes, time is almost up.
Oh no.
Oh no, we're having so much fun with math, right? But you don't want to take too much time. Like, you know, you can't spend hours and hours on one subject because it just doesn't stay with you, right? So an hour is probably like a perfect time for, you know, the amount of time you want to spend on it. So that's commutative property.
Wait, one question. Are you a teacher?
Yes. Am I a teacher? I might be. Yeah, I'm a teacher. Sure. Is that good? Hopefully.
I don't know.
Yeah, I've been teaching for a long time. I mostly teach high school now, but this is more like you guys are going to be taking more. This is more of an advanced look at math for you guys.
Yeah, because right now I'm just in grade 5.
You're in grade 5. Okay. So, yeah, we are out of time for this.
You've been a teacher for over 25 years?
Yeah, for a while.
I've been alive.
Yeah, I figured that. You're in grade 5. So if you guys are, you know, interested in this math, definitely talk to the people at StudyBNB and get set up for maybe pre-algebra class, which hopefully is going to start next week if you guys all want to join and learn some more about the basics of math and how things work. And yeah, so that's all for today. And hopefully I see you guys next week.
Bye.
Bye.